In certain types of organic molecule, electrons are able to spread out over multiple atoms in order to stabilize the overall system. This will require conjugation, in which orbitals are aligned in patterns that allow for extended interaction. For example, between non-bonding electrons and pi bonds, or pi bonds and MTP orbitals. The two examples below show a localized lone pair, where the non-bonding electrons are located only on the oxygen atom, and a delocalized system, where the lone pair is shared between oxygen and carbon. The presence of the pi system is essential for electron delocalization, and spreading the electron density stabilizes the charge and the molecule. There are really only three patterns involved with delocalizing a pair of electrons. Here we will call them patterns A, B, and C. To recognize resonance in a charged molecule, it must contain an electron source and an electron sink. The former is either a non-bonded lone pair or a pi bond. The latter is usually an atom capable of accepting a lone pair. For example, a second-row element or an MTP orbital. Typical examples are shown below for allyl-type anions, with the electron source being a lone pair and the sink being the terminal atom of the pi bond. The double-headed arrows may be used to describe the spreading of electron density in each case. This will be referred to as pattern A throughout. For allyl-cation systems, we are looking at an electron deficiency and not an electron excess as with the above anionic molecules. Here, on the left, the sink atom, usually carbon, has lost a pair of electrons from its octet, however conjugation to a pi bond allows for stabilization through delocalization. Again, we are looking at a three-atom allyl-type system, but the direction of electron spreading is reversed compared to the anions. This is pattern B. In the example on the right, the carbocation is directly attached to a heteroatom that has non-bonding electrons available to share. In such cases, only two atoms are involved in resonance, however the principle of the electron donor and electron sink still applies. This is referred to as pattern C. The allyl radical is a related species that features a half-filled p orbital on carbon, such that carbon has 7 electrons. Having a neighboring pi bond will stabilize this species in a similar way to the allyl cation, except only one electron is needed to help stabilize the radical. The second pi bond electron must therefore be accounted for in the second resonance structure by placing it on the third carbon of the allyl system. The typical allyl radical resonance structures are shown below on the left, along with an orbital representation showing how the conjugated p orbitals interact. Once we have the basic patterns established, we are able to apply them to seemingly complicated systems. Beginning with the allyl cation, delocalization across the three-atom system is often buried inside bigger molecules. The allyl system reveals itself as we draw each resonance structure. If we view the drawing of resonance structures as a method for finding out the overall electronic structure of a molecule, the following approach works well and allows us to draw an accurate resonance hybrid. Given the first structure, we notice the allyl cation at the end of the chain. So, we apply the same reasoning from the simple three-atom structure and the second resonance structure becomes apparent. We focus on the subset of atoms and what needs to be done. Using this reasoning, we work our way along the chain until we run out of pi bonds. From there, we have the required structures to complete the resonance hybrid. Notice that the partial positive charges are only placed on atoms that carried a positive charge in the resonance structures. When we switch to the allyl anion, we now must be aware of the fact that we are dealing with an electron excess and not a deficiency like with carbocations or radicals. However, the same method may be used to predict resonance structures and then construct a resonance hybrid. In the allyl anion, the electron excess is spread across the three atoms by orbital overlap with the pi system. Again, the allyl pattern is usually buried in a more complicated structure, however systematic analysis of the buried allyl subunits leads to a detailed hybrid. Once the hybrid has been built, the electron excess is then spread onto the atoms that possessed a negative charge in the individual resonance structures. The heteroatom stabilized carbocation shows up a lot in the second semester as well as in biological chemistry. Since heteroatoms such as oxygen, nitrogen, chlorine, and sulfur have extra non-bonding electrons in the form of lone pairs, they are able to share their electron excess with an electron per carbocation. This is pattern C, and it is related to pattern A, in which a spare pair of electrons helps to stabilize the adjacent 6-electron carbon. There are many structures, however, that combine carbocation patterns. Here the carbocation is stabilized by allylic delocalization as well as heteroatom stabilization from oxygen. The overall hybrid structure then reflects the spreading of the charge over the relevant atoms. The allyl radical has similar characteristics to the allyl carbocation since the radical is also electron deficient. Adjacent pi systems will help to stabilize the radical and will be found buried in more complicated situations. Applying the same methodical approach will reveal each resonance structure and make the drawing of an accurate hybrid possible. Again, the electron deficiency is only spread over atoms that have radical character in the individual resonance structures.